Okay, let's get started. So, in the previous class, we learned about the pipelining. Actually, we learned about the analogy of pipelining. So I said that the pipelining idea is developed for improving the performance of processor. So, what was the performance issue in the single cycle processor? The single cycle processor has long critical path. So it means that it's a long delay for executing instructions. Because like this, actually this is similar to the single cycle processor architecture. So which means that this is the instruction. So task A, B, C, D is similar to the instruction given to the processor, and then single cycle processor need to wait until the one instruction completes its execution. Okay, which means that it takes a long time to complete the instruction. So actually, in order to execute these four instructions, the four tasks in this analogy, but in order to complete the four tasks or four instructions, and it takes a very long time. So, and then what is the pipelining? So pipelining, when the pipelining idea is applied to the processor architecture, and we can split each step of executing instruction into the multiple steps. Actually, we learned about the 5 steps for executing instructions. So we can split these multiple steps into, and then when the one step is completed, then the task is sent to the next step, and then if this task is sent to the next step, then we can use this hardware, the hardware component. So this hardware component can receive next task, like another instruction, then and this hardware can be used for executing this task or this instruction. So that is the idea of pipeline. Actually, as you can see, if the pipeline architecture is applied to the processor design, then we can reduce the execution time. Why? So we learn in this class. So when you learn about the single cycle processor architecture, so I explained that this single cycle processor has 5 steps for executing instruction, like instruction fetch, ID, instruction decoding, execution, memory, and write back. So when a pipeline idea is applied to the processor design, then we will split the required 5 steps into the 5 stages of pipeline. So these are 5 steps for executing instruction, and then when a pipeline idea is applied, these steps can be 5 stages of pipeline. So stage means that it's like this step. Okay. Then what's the benefit? What's the benefit of this pipeline design? We can reduce the delay of the critical path, the delay of the longest path for executing instruction. So this is the example. So actually, this example is very similar to the last problem of the midterm exam, right? So this example shows the delay of each step. So which means that for the instruction fetch, we need 200 picosecond, 0.2 nanosecond. And then for register read, we require 100 picosecond like this. Then, so we can split these steps. So as you can see, there are 5 steps for executing instruction. So which means that it's like it's instruction batch, instruction decoding, execution, and memory. This is the write back. So for each step, so it will take the 200 picosecond, 100 picosecond like this. So if we design a single cycle processor architecture, then load instruction, like the load word. So load word will take 800 picosecond because load word requires is 5 steps for executing load word instruction. Okay, so we need to add the O delay of these 5 steps for executing load word. But how about the other instruction? Okay, the store word, and then other argument, arithmetic instruction, and PQ. So as you can see, actually those load word need to use the ALU for computing the target address, and then also the load word need to access the data memory, right? And then store word does not have a write back step. So the delay of the store word is the 700 picosecond. Then argument does not. If the argument instruction is executed, argument instruction does not access data memory. So this part is reduced. So we can know that the critical path for executing instruction is the load word. It's the delay for load word. So, and the clock period of the processor, the single cycle processor is determined by the longest delay for executing a single instruction. I said the longest instruction. So load word, the delay of the load word besides the clock period of the single cycle processor. Then if the if a pipeline idea is applied, then we can split these 5 steps into the 5 stages of pipeline architecture, the 5 stages. Then if we apply the pipelining, then so the instruction first step of this instruction is completed, then this instruction is given to the next stage. Then the next instruction can be given to the first stage of the pipeline architecture. Okay, so then what is the critical path? That is the longest delay for this pipeline architecture. So I said that, so this is some instruction, instruction. So instruction completes the instruction that step. So it's the instruction that stage of the pipeline architecture. Then this instruction is given to the next stage. Then instruction fetch stage can receive next instruction. So we need to focus on the delay of the only one stage. So which means that delay of this one stage besides the clock period of the pipeline processor. Okay. Then what is the clock period? So if we see the delay of each step, so each stage, then the longest delay of the stages is 200 picosecond. Okay, because so it's 200 picosecond, it's 200 picosecond, and 200 picosecond. So which means that the one stage of pipelining can be completed in 200 picosecond. So we can decide the clock period of the pipelining architecture based on this information. The clock period becomes the 200 picosecond. It is because if we just focus on the instruction fetch stage, the instruction fetch stage can receive instruction every 200 picosecond, right? This every 200 picosecond is equivalent to the clock period of the pipeline architecture. And what is the benefit? The benefit is, so compared to the single cycle processor, which have the 800 picosecond of clock period, what is the benefit? TC is reduced. The clock period is reduced. So the execution time is the instruction count and CPI, and then multiply by TC. So actually, the instruction count is determined by software and ISA and compiler. So, and then we are talking about the hardware of the processor. So actually, instruction count is the same. And then see how about the CPI. So if we just consider about the CPI of these multiple instructions, so we can know that even a pipeline idea is applied, this pipeline processor can receive instructions every clock. So a single instruction every clock, right? So CPI is 1. It's similar to it's the same to the single cycle processor. So actually CPI is not 1 for the pipeline processor. So we will learn why that is class. But for the ideal case, CPI is the 1 for the ideal case. Okay. And TC is reduced. The clock period is reduced because the longest delay is reduced with the pipeline architecture because its steps are. So actually, this longest delay, the 500 picosecond, is divided into the multiple stages of pipeline architecture. So in this example, the clock period is reduced by 1/4. So ideally, if this pipeline architecture is applied, the speed up by pipeline architecture is the 4, right? Because the clock period is reduced. So this is the benefit of the pipeline architecture. Oh, it's a very good idea, right? So this is the how the instructions are executed in the single cycle processor and the pipeline processor. So as you can see, for the single cycle processor, the clock period is the 800 picosecond. If we use the previous configuration, then in order to execute the one instruction, this processor will take 800 picosecond. But if the pipeline architecture is applied, and we know that the longest delay is the 200 picosecond, so which means that this processor can receive an instruction every clock. Okay, so for the first 200 picosecond, the load instruction is executed for instruction fetch step, and then in the next 200 picosecond, then the load instruction is executed for id step, and then at the same time period, then the next instruction is in the instruction fetch stage. Okay, that is the benefit of the pipeline architecture. So we can know that if the pipeline architecture is applied, the clock period can be reduced. So we can calculate the speedup. It's the ideal speedup by pipeline architecture. So I said ideal. So which means that in reality, so we cannot reach this ideal speedup. But ideally, if the pipeline idea is applied, then we can improve the performance of the single cycle process because we can reduce this clock period. Okay, and then also you need to remember that the clock period of this pipeline architecture is determined by longest delay of the stage. Okay. So what does that mean? So actually, the longest delay of the single cycle processor is the 800 picosecond. So if we use this configuration, and then we split this single cycle processor design into the 5 stages. So then if this delay is balanced, then it's divided by 5 is the 160. So if the hardware delay, the delay of the data path is well balanced for each step, then this state each stage will have the same hardware delay. Okay, if the delay is well balanced. So in this case, then the delay should be 160 picosecond. But as you can see, the delay is not well balanced for this example. So actually, the longest delay is the 200 picosecond. And then, like some data, as we learned from the data system design, the longest delay determines the clock period. So the clock period becomes the 200 picosecond. So even though the 800 picosecond is divided by the single cycle processor, which have the 800 picosecond of the clock period, is divided into the 5 stages, but the clock period of this pipeline processor becomes the 200 picosecond. Okay, but if the delay of each stage is ideally balanced, then we can reduce up to 160 picosecond. Okay, the speed up is 5. So this is the expected speed up by a pipeline architecture. So then
페이지별로 파이프라이닝을 하는 게 아니라 페이지 내에서 파이프라이닝을 해서 유저 의미로 밸런스를 맞춰줄 수 있는.
then so yeah, 그거는 일단 우리가 이제 하드웨어를 어떻게 잘릴 수 있느냐 그런 문제긴 한데 그거를 또 이렇게 다 밸런스를 맞추기 힘들죠. So his question is that if the hardware delay is not well balanced, so like this example, so we can find that the ID step has the only 100 picosecond and the instruction fetch stage has the 200 picosecond. Then, so ideally we can split the instruction fetch stage and then reduce the read step like the 150 picosecond and 150 picosecond, right? Ideally, but it's not possible because when the data path of the single cycle processor is designed, then the critical delay of this instruction fetch stage is determined by instruction memory, and then we cannot split this instruction memory hardware, right? So ideally we can balance the delay of each step and is what the hardware. We cannot divide the hardware into the two parts only. So we cannot apply this balanced delay. Okay. But so when I mentioned this pipeline idea, so I said that the pipeline idea is a very good idea because we can improve the performance. Okay. But when I mentioned the execution time of the pipeline architecture, I C multiplied by CPI, and then multiplied by TC. So I see the instruction count is determined by only software. So, okay. So I see it's the same. And then also I mentioned that the CPI of the pipeline architecture is 1 only if for the ideal case. Okay. Which means that in reality, the CPI of the pipeline architecture is not 1. Why? Actually, we can reduce the TC. Why? Because hazard. So actually, this hazard is the very critical issues in the pipeline architecture. So think like the single cycle process design. So actually, the single cycle processor receive the instruction, and then during the 1 clock period, then single cycle processor completes the execution of the instruction. So when we learned about the definition of the processor, like this one, the processor. So this is the processor, and then processor receives instruction, and then when the instruction is executed, then the stage of the processor are changed, and then instruction change the register file or memory, right? That's what we learned in the chapter 2 and also the start of the chapter 4. How about the single cycle processor? When an instruction is given to a single cycle processor, then single cycle processor completes the execution of instruction within 1 clock. So which means that this stage, the register file or memory are changed within 1 clock. And then the next instruction can use this changed data in register file or memory, okay, in the next clock. That is the single cycle processor. But unfortunately, if a pipelining idea is applied to the process of design, then the clock cycles can be wasted. Okay. So in a single cycle process of the CPI is 1. And then if the clock cycles are wasted, so which means that during the 1 clock, this processor can not receive the next input because the clock cycles are wasted. Then the CPI is bigger than 1. Okay. Then why the clock cycles are wasted? Because of these issues. So the hazard is the very critical issue in the architecture design. What is the hazard? Actually, the hazard means that the meaning of the hazard is like it's a load, the common load, and then if there are some cracks or some like crack, then actually this crack is called a hazard in our real life. Okay, it's like some uncommon case or some hurdles or some obstacles in the road. Okay, those are called hazard, the crack in the plain road. But the hazard in a process architecture mean is the some events that wasted some event that cause waste of cycles. Okay, so that is the definition of hazard. Okay, so what does that mean? So when I explain about the performance of the computer processor, then I explained that we assume that a processor can receive an instruction every clock cycle. Okay, that is same to the behavior of single cycle processor. But because of a certain reason, a processor cannot receive an instruction. So in this case, the clock cycles are wasted, then this event is called a hazard. Okay, so just remember the definition of the hazard. If the clock cycles are wasted in a processor, then these events are called hazard. And then based on the reasons of waste of clock cycles, we can classify hazard as the structure hazard and data hazard and control hazard. So you can find that with the structure, data, and control. So I said we can classify the kind of hazard based on the reasons of waste of clock. Okay, so what does that mean? So the first word explains the reasons of hazard. Okay, so this is also very important. So you need to understand why hazard happens in the processor, and then so we can classify hazard into the three types of hazard in the process of design. But also this is very important for some research or study, because if we know the reasons of performance degradation, then we can possibly solve these issues. If we know the reason, then we can possibly solve the issues or problems, right? Then I will explain the reasons of these three types of hazard. The first kind of hazard is the structure hazard. Okay, the structure. So structure hazard are caused by lack of hardware resources. Okay, so what does that mean? So it is caused by lack of available hardware resources. So hardware has the limited resources, right? So like the hardware resources, like the port of the register file. And then if these hardware resources are occupied by some instruction, then another instruction cannot use its hardware, right? Because hardware resources are limited. So structure hazards are caused by its limited hardware resources. So for example, this is the adder, okay? So, and then, so actually ALU. And then when the BQ is executed, then BQ need to use the ALU for the X1 minus X2, okay, right? So in order to compare the two operands, then BQ needs to perform subtraction. And actually, BQ also need to use adder for PC plus target, right? But if this adder does not exist in the processor, then BQ needs to ALU for this add operation, right? That's why in the single cycle processor, we use the additional adder for the PQ instruction, right? So if there is only ALU, then PQ needs to use the ALU for the subtraction operation for one clock, and PQ needs to use ALU for this add operation for the next clock, which means that BQ needs to occupy ALU for 2 cycles. And the ALU is occupied by BQ during 4 cycles, then the next instruction cannot use this ALU, right? Then clock cycles are wasted. So this kind of hazard is called the structure hazard. Structure hazard is that because of the limited hardware resources, the clock cycles can be wasted, and this kind of hazard are called the structure hazard. Fortunately, our processor design does not exhibit any structure hazard, right? So actually, when we run the single cycle processor, we add the additional adder for the BQ. So our processor design does not exhibit any structure hazard. And what is the data hazard? So data, if we see this data hazard, so this first word represents the causes of hazard. So data hazard is caused by data dependencies. So what does that mean? Like add x1, x2, x3, and then the next instruction, and next instruction, then here we go, x4, x1, x5. Actually, we use this type of statement or this type of computation, right? So if we see this two instruction, this following instruction needs the result from the former instruction, right? But we already know that the result of this add instruction is returned to the register file in write back stage, write back step actually in a single cycle processor. And what's the problem? Problem is that this is another example. This is the add, and then this is the sub, and then the x19 is updated by this add instruction, and then this x19 is used by sub instruction. But if we see the pipeline stage of this add instruction and sub instruction, the result is written back during this time period with the write back stage. But when the sub instruction is executed, and the sub instruction originally in the instruction fetch and then ID here, sub instruction need to read data x19 during this period. What's the problem? Sub instruction, the following sub instruction try to read operands from register 5 during this time period, but this data is not ready. This data does not exist in the register file, right? Because the data will be return back during this time period, the multiple spaces. So this is the future and this is the past. So actually, this solve instruction cannot receive data from future, right? So what does that mean? Solve instruction needs to wait until this data is returned back to the register file. So in a single cycle processor, so this problem does not happen, right? Because during the one clock period, the formal instruction completes right back to the register file. Then the next instruction can read this written back data from the register file, right? But in a pipeline architecture, the write back is the last step, the last stage. And then this time, and you consider the timing of this write back. The write back is the future. Okay, which means that solve instruction need to until the data is written back to the register file. So clock cycles are wasted. Okay, this kind of hazard is called the data hazard. So data hazard is caused by data dependencies, also the timing of the write back, and then the register read, also timing of the data hazard is caused by the timing of the write, and then timing of read during between two instructions. Actually, data hazard is very critical for the performance of the computer system, right? It is because when you write the program, so we write the program like the A equal 1, B equal 2, and then C equal A plus B, like this. So which means that actually the following statement requires the data from the former instruction. Okay, you can write the program like this. So actually data dependencies are frequently observed in our normal application. And then because of these data dependencies, clock cycles can be wasted. So this hazard is called the data hazard. So actually very critical issue in process architecture design.
슬라이드 위치에서
네.
버블이 다른 인스트럭션을 배치돼서 사이클의 단계가 없을 때도 해줘더라고.
그렇죠. 네. So if the site, so this question is that if there are some independent instructions like the other instructions, so this is if there are some independent instructions or and then if these instructions are not dependent on this formal instruction, which means that if the data dependencies are not observed, then these instructions can be executed without waste of clock. And this is not called the data hazard, right? Because the clock cycles are not wasted. So hazard. So just to remember the definition of the hazard. Hazard means the events that cause waste of clock, which means that if the clock cycles are not wasted, this is not called the hazard. Okay, good question. And then control hazard. So if we see the control hazard, then we can know that, oh, this control hazard is caused by control. So which means that control instructions like PQ, branch instruction, and jump instructions. Why? So when these instructions are executed, then program counter is changing. But when the program counter is changing, like actually where is the example? So, under this BQ is executed, then actually we can know the target program counter of this BQ at the EX stage, right? Because during the IV stage, the BQ release operands from the register 5, and then during the EX stage, BQ calculate the target program counter. And then actually the behavior is changed, behavior is diverse. So which means that if the branch is true, then the PC should be changing. But if the branch is false, then PC is the PC plus 4. So which means that if the branch is true, then PC is changed at the next stage, then the new instruction should be fetched by this changed program counter. So which means that we need to wait until the result of a branch instruction is resolved. Okay. So which means that we need to wait. Which means clock cycles are wasted. And this kind of hazard is called the control hazard. So the control hazard. So control hazard means the waste of clock cycles because of control instructions like branch or jump instructions. Okay, so this is called the control hazard. Okay, so there are three kinds of hazard in the process of design. So, and then when a pipeline architecture is applied, then we need to consider this hazard. Why? Because of performance, like instruction count, API, and then PC. So with the pipeline architecture, then we can reduce the PC. And the instruction count is the same. But how about the CPI? I said hazards are events that waste the clock cycles. So which means that if the clock cycles are wasted by hazard, then CPI will be bigger than 1. If the CPI is increased, then execution time is also increased and performance is reduced. So that's why we need to avoid hazard in our process of design. It's very critical. It's very important. Okay. So I explain about the structure hazard and data hazard. Then I will briefly explain about how to solve the hazard. Okay. Then first, structure hazard. How can we solve the structure hazard? So I said that if we know the reasons of problem, then we can approximately solve this problem. So what are the reasons of structure hazard? It's the limited hardware resources. Then how can you solve the structure hazard? If we use more hardware resources, then we can solve the structure hazard, right? So what does that mean? Like the branch instruction, BQ. BQ instruction requires the sub and add operation. So when the BQ is executed, we apply sub instructions using ALU, and we can add adder. Right. The hardware is the more hardware is included in our process of design, then we can solve the structure hazard. So another example is actually instruction memory and data memory. So in chapter 2, I explained that instructions are also data, and then we store instructions and all data in the main memory. But when I explain about the single cycle processor architecture, this single cycle processor has two memory components: instruction memory and data memory. Actually, why? Because we want to avoid structure hazard. What does that mean? Actually, the instruction memory, so actually every instruction accepted instruction memory. This is because we require it to instruct, we require it to read instructions from the memory, so which means that in order to execute the instruction, then we need to access memory. So every instruction needs to access the memory. Okay. And how about the data memory? Data memory is accessed by load or store instruction only, right? So what's the problem? If the load or store instructions are executed, then this load word or store word need to access memory twice, 2 times, right? So firstly, then we need to read instruction from memory, and then the store word or load word need to access the memory. So these memory instructions need to access memory component twice. So which means that if a single cycle processor has only one memory component, then when the store word or load word are executed, then it will consume 2 cycles. Okay? So we want to avoid this case. That's why the single cycle processor, when the single cycle processor is designed, there are 2 memory components, like instruction memory, because the instruction memory is accessed by every instruction. And then store word or load word instruction is the additional accesses for data access. So we add another memory for this store word or load word instruction. Okay, so we can solve the structure hazard by adding more hardware resources, right? And then data hazard. So I said that data hazards are caused by data dependencies in our program, actually. Then how can we solve this data hazard? So actually, these are the compiled instructions, and the hardware cannot change these compiled instructions, right? So just compiled, and then these instructions are stored in the memory. It cannot change. But how can we solve the data hazard with hardware? Forging, data forging. So what does that mean? If we see the, if we check when the data is generated by instruction, then we can solve the data hazard. So just to see this example, so this is the former instruction, the add x1, x2, x3, and then the following instruction is the sum x4, x1, x5. So as you can see, this x1 is used by sum instruction. Oh, which means that it's the instruction fetch, instruction decoding, execution, memory, and write back. And this add instruction is executed, then we know that during this write back stage, the result of add instruction is stored in the register file. But when is result generated? So actually this result is stored during the write-back stage, but we know that the result is generated at the EX stage, right? Because this is add instruction, and then actually this is the X2 and X3, and then the result of X1 is already generated at the EX stage. So what does that mean? Hardware already has result data, but this result data is not written back to the register file yet. But hardware already, the processor already has result data, right? If we have already the result, then we can use this result, right? So data body means that the result is already generated by ALU, and then when this result is used, so actually this is the sub instruction. Sub instruction require this result during EX stage of the sub instruction, right? This is the next class of the EX stage of the add instruction. Are you following me? So the result of add instruction is generated at this point, this time point, and this is the EX stage of the sub instruction. This result is required at this point. So if we just compare the timing of this result and then this point, then we can know that, oh, this is the past and this is the future. So which means that hardware, when this value, so the result of the add instruction is required, processor already has this result. Then this result can be delivered to this point, the input of the ALU. Okay, so if this data is required, then this data is already existing in the processor, and then existing data can be forwarded into the input of ALU. This technique is called the data forwarding. Okay, so if we just compare when the data is generated and when the data is required, then we can apply the data forwarding. Okay, but if the formal instruction is loaded, so if the formal instruction is the R-type arithmetic or logical instruction, then the result of this instruction is generated after the ALU, so which means that the late part of the EX stage. But if the formal instruction is a load instruction, then actually the result of this load instruction is generated at this point, right? So if the load instruction is executed, then this load instruction needs to address data memory. So it's the memory stage, during the memory stage, okay? And then in the late part of the memory stage, the result of the load instruction is generated. Which means that if the sub instruction is executed like the instruction fetch, instruction decoding, and then EX. Then this sub instruction requires data of this load instruction at the early part of the EX stage. Okay, at this point. So if we just compare the timing, so actually the result is generated at this point, and then if the sub instruction is executed with a hazard, then the sub instruction needs to read sub instruction requires data at this point. What's the problem? Oh, this is future and this is past. So this is not possible. Understand? So in this case, if the former instruction is the load instruction, then the following instruction requires data from this load instruction. The clock cycle should be wasted. So because the former instruction is the load instruction, we cannot avoid this hazard. Okay, so this hazard is called the load use data hazard, which means that the following instruction requires data from the former load instruction. So the pipeline processor cannot avoid this type of hazard. So one cycle is wasted because of data dependencies between load and following instructions. So how do you cannot solve this problem? But compiler can solve this problem. Not always, but if possible. So what does that mean? So we can apply the compiler optimization. So which means that if you see that this code, if this is the original code, then you can find that, oh, this is the load instruction, and this is the load instruction also. And then the following add instruction requires the data from this load instruction. And then, you can find the data dependency. So former instruction is the load instruction, and then the next instruction requires data from the former load instruction. Then we know that, the one clock cycle is wasted. It's the data hazard. Also, another data dependency is observed, like this load and the add instruction. We can find data dependency between this load and add instruction, or one cycle is wasted. So because of the data hazard between load and add instruction, then two cycles are wasted. So this code. What? If we change the order of instruction, then we can solve this data hazard. But this should be done by compiler, not hardware. So this is the compiler optimization technique. So actually, inside of the base class, the compiler can change the order of instruction if there is no data dependency is observed. What does that mean? So we can find data dependence between this load and add instruction, but we cannot find any data dependencies between this load and then this add instruction. Okay, so what does that mean? This load instruction can be located before add instruction, right? Because there is no data dependencies between this add and this load instruction, right? The result of this load instruction is the X4, but this add instruction does not require any data from this load instruction, which means that the load instruction can be here. In this case, So after this load instruction, the next instruction is the load instruction. So clock cycle is not wasted. And then the add instruction is here. So because the distance between this load and add instruction is one instruction, so one cycle, then we don't need to store this add instruction. So this is the compiler optimization. Compiler can change the order of instruction if the data dependency is not observed. Then by doing this, we can solve the data hazard. So another data hazard are also reserved because we can observe the data hazard between this load and add instruction, but this load is moved up to this add instruction. So we can find that the distance between this load and this add is the 2 cycles. So no data hazard. Okay. So if possible, the compiler can change the order of instructions to avoid data hazard. So it's not already possible. If we find the independent instruction, then we can change the order of instruction. But if not, we cannot change the order of instruction. Okay. And then control hazard. The control hazard is very critical, also very critical performance issue. Actually, when the branch is taken, or conditioning that the condition of the branch is true, then PC is changed to the target of the branch instruction. Then we cannot avoid control hazard. So actually, the processor applies the branch prediction technique. So it's just a prediction to reduce the control hazard. But actually, the branch prediction ideas are widely used for the modern processors. So in this case, in this time, I will skip the explanation. Skip the explanation regarding branch prediction. But we can reduce the control hazard by using branch prediction. Okay, I will explain later. So pipeline. So we learned that the pipeline is good for improving the performance because we can split the required steps to the multiple stages of the pipeline architecture. So by doing this, we can reduce the theory. But when a pipeline architecture is applied, then clock cycles can be wasted due to hazard. So we need to reduce the hazard as much as possible. Okay? So there are 3 kinds of hazard: structure, data, and control. This is very important in the process of design. Okay, so please understand the causes of hazard. Okay, so I briefly explain about the pipelining of the process of design. Then let's see how the pipelining is applied to our process of design. So as you can see, this is the single cycle process of design we learned in the previous chapter, in the previous topic. So we can split each step of the single cycle process into the 5 steps, like instruction fetch, instruction decoding, and then EX, and then memory, and then write back. Okay. So as you can see, during the instruction fetch stage, the instruction is read from the instruction memory. And then during the instruction decoding, the operands are read from the register file. Also, the instructions are decoded. And then during the EX stage, using the operands, then the ALU performs the required operation. Then during the memory stage, the load word or store word access the data memory. And then during the write back, the result is written back to the register file, right? So this is the structure of the single cycle processor. Then how can you implement the pipeline architecture? Oh, there are 5 steps here. Here are 5 steps. 5 steps here. Oh, we can split. Split. Then it's okay. It's actually not. So it's a hardware. So we need to build the appropriate hardware for pipeline architecture. How can you split them? How can you split the stages, the pipeline stages? So in a single cycle processor, the clock cycle looks like this, right? So during the instruction fetch step and then write back, the clock cycle looks like this. But in the pipeline architecture, the we split is one stage of the single cycle processor into the multiple stages. So which means that the clock cycle looks like this. So what does it mean? So when we learned about the conventions of the digital design, then I explained that digital design is digital design system looks like this. So this is the combinational logic, and then you can find the T flip-flop, then T flip-flop from at the beginning of the combinational logic, and then the output of the combinational logic, and then the clock is given to these T flip-flops. So clock cycles looks like this. So during this clock period, the combination logic generates the output from the input signals. So this is the basic design of the digital system. Then how can we implement the pipeline architecture? The same. The pipeline architecture, the clock period is determined within this step, so this stage. So which means that after these are hardware component, so it is a combinational logic. So after this component, we can get the result of the hardware component. And then these results are sampled by clock signal. Okay, so what is required? T flip-flops are required. What does that mean? In the pipeline design, okay, so actually these are T flip-flops. These are T flip-flops sampled by contain clock signal. Okay, and then the output of these hardware components are sampled by these T flip-flops. And then in the next clock, this output is given to the next stage. Okay, are you following me? So it looks like this. So this is T flip-flop, and then this is the combinational logic 1, and then this is also another T flip-flop, and then this is the combinational logic 2. And then as you can see, this combinational logic 2 receives the data from the combinational logic 1. But you can find that there is a P flip-flop between the CL combination logic 1 and the combination logic 2. So we can reduce the clock period because the critical path is critical path is reduced. It's the same to the pipeline design. So as I mentioned, and the operation of this stage is complete, then the result is delivered to the next stage. But this data delivery is controlled by clock signals. So this is the instruction fetch stage. So the output of the instruction fetch stage is this output. So these outputs are also sampled by clock signal, and then in the next cycle, the results are delivered to the EX stage. Okay, this is instruction coding, and then also it's the same. These are output. Then these output of the execution stage is given to the memory stage at the next cycle. Okay. So what is required? What are required? We require D flip-flops, and then actually these D flip-flops are called the pipeline register. Pipeline registers. So this register these registers are different from general purpose register over RISC-V. So actually these registers are actually D flip-flop, but the signals are temporarily stored. The output signals are temporarily stored, and then at the rising edge of the clock, these signals are updated to for the next stage. So that's why these registers, these flip-flops are called the registers. But you need to remember that these registers are different from the general purpose registers of RISC-V. So actually, these registers are D flip-flops. So just means that the sample the output signals of this stage, and then hold these values during for the next stage. Okay, so these are just D flip-flops. And then we can represent this pipeline register like the instruction fetch /ID. So which means that if we write the register like this, so which means that this is the pipelining register between instruction fetch and ID stage. Okay, so I will use represent this convention for representing pipelining register. Okay, so if I write EX and MEM, which means that this is the pipeline register between EX stage and memory stage, right? Okay, so you can split each stage using the D flip-flops, which means that you can split each step of a single cycle processor using pipelining registers. Okay, so which means the signals are sampled by clock signal, and then in the next clock, the signals are the signal values are held by these D flip-flops, and then it is given to the data path element for next stage. Okay. Okay, so I will stop here. Then so actually we need to also consider the timing of the clock signal. That's why so pipelining architecture is very good idea. So as I mentioned, we can dramatically improve the performance of a processor using pipelining. But structure is more complex. Okay, so I hope you can understand how the pipelining implemented in the process design. Okay. So in the next class, so I also explain about the pipeline architecture of the RISC-V and then how the signals are delivered and then how the signals flow through the pipelining stages. Okay. So any questions? Thank you for your attention and then see you in the next class. 감사합니다.